So I've got a long version of this talk and a short version. Which one do you want? Yeah, I know some of you got dinner. Right, so thank you very much for the extremely kind invitation to come here. So as you can see, my affiliation is Birmingham. And of course, in a small way, the Nobel Prize touched Birmingham. And I thought I should come here and find out what the fuss was about. And it's been 3 days of, well, a bit of an intellectual nosebleed. I have climbed to such heights, but thoroughly enjoyable. So thank you very much indeed. In fact, my strongest and lasting impression was actually the photograph that you showed, John, which was Mike stuck halfway up a mountain. That, I think, was truly impressive. Right, so I'm going to try and answer this question here. So, topology in nuclei. And it may be that you don't actually care whether topology exists in nuclei or not. So I'm going to try and lift your engagement a touch. And I'm going to try and make the argument, so this is a bit of a bold argument, and it might have an element of tongue-in-cheek, that topology is linked to the origins of life, or at least organic life. Okay, and you can test me whether I succeed against delivering against that at the end. So this is a region of nuclei, so it's light nuclei. You can see we are going through some isotopes here of helium, lithium, beryllium, boron, and carbon. And you can see by the slightly crazy pictures there that actually light nuclei have a very rich range of structures. So if I just guide you through some of those structures. So you will see, for example, if we follow this line here, this is called the neutron drip line. And as we go along the neutron drip line, we see that if we follow the lithium isotopes, that we get to lithium-9, and then lithium-10 doesn't exist, and then lithium-11 does. And what happens in the case of lithium-11, actually, it's a very weakly bound system. So you've got a lithium-9 core plus 2 S-wave neutrons, and those S-wave neutrons are very weakly bound, loosely bound. So in fact, this nucleus, which has only 3 protons, this weak binding means that the size of the nucleus is that of lead-208, so 82 protons. And if you remove one of those neutrons, then the remaining nucleus, clearly lithium-10, disintegrates. And if you were to remove the lithium-9 core, the two neutrons that are left behind, and that's an unbound system. And so the whole thing disintegrates if you remove any one of those 3 components. And that's represented by these links here. All of these nuclei are what are called Brownian nuclei. So there's the first piece of topology. There's, as we go along here, you can see all sorts of other kinds of structures, and we'll encounter those in a little bit more detail. But I just want to show you the spinning thing at the top. That is carbon-10. Carbon-10 is a rather unusual nucleus. There's only one example in nature where this happens. Let's call it a Brownian nucleus. It's a nucleus which, in terms of links, is of order 4. It is composed of these components here. So we have helium, helium, proton, and proton. And if you remove now any one of those components, if I take a proton out, I have boron-9. That spontaneously decays. If I take 2 protons out, I've got beryllium-8. That spontaneously decays. If I remove an alpha particle, I've got beryllium-6. That spontaneously decays. This nucleus is completely balanced by the properties of these 4 particles. Any one of them removed the whole thing falls apart. And it's...
And what happens if you remove something in the EPU?
Okay, that costs you a huge amount of energy to do that. So it's not relevant. These kinds of nuclei provide some of the best tests of our understanding of nuclear structure. But you can see the topology influence. So here is actually the rest of nuclear physics. So the bit I've been talking about is sitting just over here. The conventional picture of nuclei is all of this stuff up here. I saw in the magazine that you got in your pack when you arrived, there was some discussion of element 118 discovered in Dubna by Yuri Oganessian. That's right up at the top there. But nuclear physics is actually these days much more broad than historically the focus was. So right down in the bottom corner here we have the QCD vacuum. That is the domain of very energetic collisions at the Large Hadron Collider, the ALICE experiment, probing the nature of QCD. And as we go up on this logarithmic scale, we come to the proton and neutron. And there, the challenge is really trying to understand what is that internal structure. And it's a little bit more than just, of course, 3 valence quarks. You've got antiquarks. You've got quark-antiquark pairs being born out of the vacuum. You've got gluons being exchanged between those quarks. So you've got a very complex system. And the test is whether one can understand how this ferment of particles here gives rise to this arrow here, which is actually when you measure the overall spin of the proton, why is it always 1/2? And one imagines that there must be some interesting topology going on inside that proton. And related to that, and all of these links here, are the nature of that strong interaction, which is, after all, the thing which is determining the mass. So the Higgs component to the mass is negligibly small. Most of the mass is derived from this complexity of the strong interaction. The challenge in nuclear physics and for nuclei like carbon-10 is, can we bridge from QCD and develop an interaction, a force which is motivated by QCD, which can describe like nuclei? Now, many of you will know that that's close to impossible. On the nuclear scale, the strong coupling constant becomes very large, and you can't use perturbation. So you need a different approach. And back in the 90s, Weinberg came up with another approach, which was chiral effective field theory. And chiral effective field theory is one where there is a broken symmetry, and associated with that broken symmetry, there's a Goldstone boson, and that Goldstone boson is a pion. And then you can describe the interaction by a field made up of a series of terms of leading order, next to leading order, etc., where the pion field gets more and more complicated. So you have pions, and then in addition, there are things called contact interactions, which then are the short-range mesons which are associated with that interaction. And that is the state of the art at the moment. So that's the best one can do in terms of QCD degrees of freedom. Here is a lovely calculation where that interaction now has been taken and put on the lattice, calculating the properties of a nucleus carbon-12. And what one sees is, rather than, so nucleons are distributed on the lattice, and then you find the lowest energy state. And these nucleons precipitate out into, in this case here, some kind of triangular arrangement. Here's another triangular arrangement, a slightly more open one. But you see the nucleons are precipitating out into pairs of protons and neutrons. And in fact, here you see the emergence of alpha particles. So that's the best that we can do at the moment. Now, as you've already heard, Birmingham's famous for many things. Tony Skirm is another, and skirmions is one of his creations. And one of his proteges, Nick Manton, at Cambridge, has taken the skirmion model and tried to apply it to nuclei. So this is where topology comes in terms of trying to understand some of the nuclei like carbon-12. So here you can see for different topological charges what the skirmionic fields look like. These are representations of the pion fields. And the interesting one is this one over here. So as well as topological charge, these correspond to different baryon numbers. And this is baryon number 4, and this would then be the alpha particle. And what Nick and his co-workers have seen is that actually, if you take this and look then at baryon number 8, you see a structure which looks like this, 2 of these put together. And for baryon number 12, you see here there's a structure which is something like a triangle. And for baryon number 16, you can see some kind of tetrahedral structure and some planar structures as well. So here we see the pion topological field, which seems to have that alpha cluster structure built into it. Now, so we could either deal with a really complex approach, so chiral effective field theory, but historically nuclei have been modeled through a mean field approach. So in the mean fields, you have some potential which simulates the motion of the protons and neutrons through the nucleus, and you solve the Schrodinger equation that gives you the nuclear shell model. The mean field approach works. So what I want to do is actually examine some of the things which come out of that mean field. So what you saw here was we're going to try and reproduce that mean field by a harmonic oscillator. I've got a very simple game I'm going to play. I'm going to take some balls and drop them into a harmonic oscillator. And that's what you see here. On the left-hand side, some balls just falling through a harmonic oscillator potential. And on the right-hand side, what happens if you now impose some short-range interaction between those balls? And you'll notice that that interaction might look a bit like a nucleon-nucleon interaction. Left-hand side looks dull. Right-hand side looks like it's got all the physics in it. It's got the physics which is about those interactions, the pairing interactions between 2 protons or two neutrons, or a proton and neutron. But actually, the left-hand side on a nuclear scale gives you some very interesting effects as well. Now, of course, this is classical, and to do it properly for nuclei, one has got to do it quantum mechanically. And here is then the solution of the harmonic oscillator. And actually, this version here is the deformed harmonic oscillator. So what we have is a harmonic oscillator potential, and you've got to think about something which is 3-dimensional, so a sphere. And now I grab that sphere and I stretch it along, let's call it the z-axis. And this is axially symmetric, so if I now stretch it along the z-axis and slice through the center and turn it around, I see a circle. So the x and y axes are equally deformed. And what you see here is how the energy levels in this deformed harmonic oscillator evolve. So no harmonic oscillator quanta, nothing happens. If I've got one oscillator quanta and that quantum appears along the z-axis, then as I stretch along the z-axis, that comes down in energy. And then the 2 oscillator quanta associated with the transverse directions, those go up in energy. And so what you see is an evolution of the harmonic oscillator levels as a function of deformation. What you also see is that if I now color in the degeneracies, so if I'm building a nucleus now, I can put 2 protons or 2 neutrons here, 6 protons, 6 neutrons here, dot, dot, dot. And if I go to 2 to 1, you can see that those degeneracies are repeated twice, 2, 2, 6, 6. And at 3 to 1, they're repeated 3 times. So this is, if you use your imagination, this is almost like at 2 to 1, you've got 2 degenerate harmonic oscillator potentials, and at 3 to 1, 3 harmonic oscillator potentials. And you will notice the characteristic h bar omega spacing here is increasing, and hence the potential size is decreasing as you go to larger deformation. So that's kind of interesting, but maybe it's no more than curious. Now, what one can do next if you want to build a nucleus is to, so let's make beryllium-8. So beryllium-8, I would put 2 protons and 2 neutrons into this level, 2 protons and 2 neutrons into this level, and I end up with a density, so take an S state and a P state, square them and sum them, which you can see this double hump structure. And if you wanted to, you could do a basis transformation. You can switch that to a 2-center basis and ask what does the wave function look like, or at least the densities, and here you can see them there. If I now go to 3 to 1, so this is making carbon 12, you can see that I get a 3-centered density. And you can explore all of this fully, and you get all of these kind of cluster patterns. And it doesn't matter where you are. So if I went to this point here, which would be 8 plus 8, 16 plus 16, no, 8 plus 8, making sulfur 32, 8 plus 8 times 2. Then you would see 2 oxygen 16s next to each other. So actually in this deformed harmonic oscillator in the mean field, you see those cluster patterns appearing as well. And you could then begin to mix degrees of freedom. So if you, alpha particles being bosons, you could think about 2 alpha particles next to each other. And then you could ask the question, what happens if I introduce additional fermions? Let's call them neutrons. What kind of structures do you get? Rather interestingly, we probably won't have time for it, you get some kind of molecular configurations. So that's some simple ideas. The alpha particle nature of nuclei is not something new. In fact, it goes back to almost the earliest days of nuclear physics. And just like there are touchstone papers in every field, here's the touchstone paper in this particular one. This is some work by Edward Teller and Hastan. It's an analysis of the binding energy of alpha particle-like nuclei as a function of potentially the number of bonds between those nuclei. So if you've got beryllium-8, you've got one bond. If you've got carbon-12, you've got 3 bonds. Oxygen-16, 3 more. And you can see that there is this linear relationship between the binding energy and the number of bonds. And in fact, if you look closely, you will see there's a jump of 4 as you go from magnesium to silicon. And you can understand that jump of 4 because if you put another alpha particle into magnesium-24, you need 4 bonds, or you make 4 bonds. And Teller not only predicted the kinds of structures, but he also predicted the spectroscopy. Now, this was at a time where very few excited states were known in nuclei. And so this was a prediction back in 1938, which actually the field in many ways has been trying to understand. So given that we've already met carbon-12, I'm going to talk a little bit more about carbon-12. And here is Teller's prediction for the spectroscopy. You see you have a ground state. Well, we'll learn about the quantum numbers in a minute, but a 0 plus ground state, G being Gerada, positive parity, and then a 3 minus state, Ungerada state over here, plus many others. Equally, we could look at oxygen-16. Now, the question is whether this is an accurate description. Is Teller's picture correct? And in the intervening time between 1938 and now, there's this contribution from Ikeda back in 1968, which said, well, actually, although the symmetries might be present in the ground states of these nuclei, if you really want to fully explore these highly correlated states, actually you want to go to states above the decay threshold. So where you put enough energy into the system that you can liberate, in this case, alpha particles. And so if we think about carbon-12, a triangular ground state, and a fully liberated 3 alpha particle excited state. In recent times, there's been a bit of dispute about the nature of these states here. You can see that you can disintegrate nuclei into, in this case, 7 alpha particles, whether such states correspond to a Bose condensate in nuclei, because the alpha particles, of course, are bosons. Right, so here we see the spectrum of carbon-12. This is the experimental spectrum. And what we're going to do is try and work out how accurate was Hafstad and Teller's prediction about the structure of carbon-12. Interestingly, right in the middle here is a very famous nuclear state. In fact, in nuclear matter, or in nuclear physics, there is only one state which bears a man's name, and that is the Hoyle state, after Fred Hoyle. Fred, of course, didn't receive a Nobel Prize. One wonders why, particularly as his co-worker Willie Fowler did, but nevertheless. But what Fred's great contribution was, it was, well, many, but one of them was to understand the alpha particle burning process, the helium burning process in red giant stars. And in the helium burning process, triple alpha process, it proceeds first by 2 alpha particles joining together to make beryllium-8. Beryllium-8 lives for 10 to the minus 16 of a second before it disintegrates. But if the density and temperature are high enough, there's a chance that you capture a 3rd alpha particle and you proceed resonantly into carbon-12 through this state here, the Hoyle state. The presence of this state at exactly the right energy raises the probability for the formation of carbon by 8 orders of magnitude. Now imagine that I had this power and I could lift the energy or lower the energy of that state, and you can see the precision of its energy there, by 50 keV, then I could make you vanish. And that might be a good thing, and it might not. So it has to have exactly the right energy in order that you exist. So why is there a state there with exactly the right quantum properties, exactly the right energy so that you exist? And does it have anything to do with topology? So to answer that last part, one has to understand the structure of that state. So what I'm going to do is walk you through how on Earth Teller could make a prediction about the spectroscopy. And he used the dynamical symmetries of this 3 alpha particle structure. Here is his equation, ripped out of his paper. There's a couple of quantum numbers here. There is a k quantum number, and you can see k is the angular momentum projection along the symmetry axis of this 3 alpha particle system. And then j is the total angular momentum. So thinking about a rotating object. So if k is equal to 0, this term here is vanished, and this vector here has gone to 0, and all of the angular momentum then is along this axis, as is shown here. And you can see effectively what you have is a beryllium-8 rotating, and hence this moment of inertia of beryllium-8 here. And the spectrum of states that you get are 0, 2, and 4. Now, the next thing that you could do, and this is the closest I'm going to get to a vortex, is now spin the 3 alpha particle system around this axis here, giving each alpha particle 1 unit of angular momentum, and 3 times 1 is 3, so we have k equals 3, and we have now something which is rotating like this, and that would give you a 3 minus, 4 minus, and 5 minus. And the way to think about this is actually, as you go to higher angular momentum, think about a spinning coin as it settles down onto the table. It's got this kind of wobbling mode. So that's the collective motion there. Now what we're missing is the Hoyle state. So how do you make a Hoyle state? So one possibility is to have a monopole excitation of that nucleus, and you see that the alpha particles, instead of being close together, are now much further away. And then, because it's a triangular configuration, you should get the same rotational pattern. What you'll notice, and this is important, is that you will get a signature, which is that you should have 2 4+ states close together with a 4-. And if you see that experimentally, then probably that's the structure. So, all right, so let's go back to what the spectrum of carbon-12 looks like. So here you see this rotation here. So there's a ground state, 2+ and 4+. And what we're going to do next is focus on trying to find the collective excitations, the rotations associated with this Hoyle state. Experimentally, by the way, I'm an experimentalist. Experimentally, the challenge is to find a 2+ state in a region here, which, as you can see, as indicated by this broad box here, there is a 0+ state, which is very broad and blocks out the experimental spectrum. So one has to find, and remember the Hoyle state was discovered back in the 1950s. So after close to 60 years, nobody had found this 2+ state, this 2+ excitation, because it was buried underneath this 0+. And so you need an experimental probe which allows you to suppress that 0+ state. This is a rather neat approach, which one takes a gamma ray beam of high energy. So only recently can we produce high energy gamma ray beams. And the way you do it is you take a laser and you backscatter that off a high energy electron. So you convert the electron energy into the photon energy. And so then you go from the ground state of carbon-12 to an excited state. Because a photon has spin 1, you cannot go from a 0+ to a 0+. So that suppresses the 0+. And then you can image the decay pattern of the carbon-12 as it decays. So here's an image of 3 alpha particles. And then you can measure the angular distributions. And one sees a lovely oscillation which tells you that you've got something with spin and parity 2+. And in fact, then you change the gamma ray energy, and you map out that resonance strength. And in fact, it's cut off here. This is some other data. So these were the data that my group took, which actually preceded these data here, which demonstrated this 2+ state existed. So we found the 2+ state. So what does that tell us, and how does it help us tell us something about the Hoyle state? Well, it can tell us because the energy separation from the 0+ state to the 2+ state tells you how deformed that structure is. So it's very deformed, then the 2+ state is very close to the Hoyle state, and vice versa. And if you have a 2+ state, then there should be a 4+ state. In some experiments in Notre Dame in the US, we managed to find the 4+ state. So we have a way of characterizing the Hoyle state, and I'll come back to what its structure looks like. And then we also look at the negative parity states, and you can do that using looking at the decay process where the state in carbon-12 decays into 3 alpha particles in the center of mass frame. So these are what's called Dalitz plots, another Birmingham legacy. And you can see for the different spin and parity states, you get different patterns here. And so we can also look at how the state decays. Does it simultaneously decay into 3 alpha particles, or does it decay sequentially? All right. And so what we've managed to do is now map out where the 2+ state is, and we know its properties. We know where the 4+ state is associated with the Hoyle state. We have the 3- state. We have the 4- state, which is up here. And one of the things I'm most proud of is that we managed also, there's the 4 states close together with 4+, 4+, and 4-. And if you want to clinch it, you have to find the 5-. And on our cyclotron in Birmingham, homemade accelerator, we have found the 5- state. And you can sit in the center of mass frame and look at the emission pattern of the alpha particles as they come out. And one sees this experimental oscillation, which tells us that we got the 5- state. So there you go. So that is a great description of the states in carbon-12. We have this rotational behavior. So we have this compact structure with the 0, 2, and 4+, and 3-, 4-, and 5-. And then we can see that we have this rotational structure associated with the Hoyle state, and its moment of inertia is much, much higher. So that tells us that we've got a much more extended state. So the last, what have I got? I've got 10 minutes. OK. All right. God, how am I going to spend 10 minutes? All right. So the last bit is, what is the structure of the Hoyle state? We've got something which is extended. But there are many calculations. You've seen this one here. This is actually an ab initio type calculation. You start with 12 particles in Gaussian wave packets with some interaction between them, something called a molecular dynamics. This was the lattice calculation. This is the harmonic oscillator or alpha cluster model. You can see a linear type arrangement, and then we've got an alpha particle condensate. Which one of these is the right description of the Hoyle state? Well, we can eliminate this one immediately. If we had a linear arrangement of alpha particles, then the 2+ state would be very close to the 0+ state. And for similar reasons, we can eliminate this one here, which leaves us with these two as a possibility. Now, if we have this structure here, we might expect, because these are 3 identical bosons, that when it decays, that each one of them is emitted with the same energy, same momentum. Whereas this thing at the top here, you can see it looks a little bit more like beryllium 8 plus alpha. So if we could measure the probability for it to decay into beryllium 8 plus alpha versus directly into 3 alpha particles, that would help us distinguish between these 2 possibilities. It's challenged by phase space. So the phase space for the direct decay is very, very small. So the probability that this decays directly into 3 alpha particles is suppressed, which means an experimental measurement is going to be very challenging. So again, here's a piece of work done on our accelerator that sits in the physics department. Just to give you a feel for how these experiments are done, what we have is an alpha particle beam traveling in this direction here. It hits some target there, and that target is made of carbon. The alpha particle bounces off, and we measure its properties in these detectors here. And then the Hoyle state, when it's populated, decays into 3 alpha particles, and we track them over there. Very simple experiment. And if you want to analyze this, what can happen? Well, if you have a sequential decay in a frame where the total energy for the decay process is equal to 1, in a sequential decay, this alpha particle will have half of that energy. Whereas if you have a decay which is democratic, direct decay process, then the alpha particles share that energy equally. So here are the alpha particle energy spectra on a scale which is from 0 to 1. And here you can see the peaks which correspond to 0.5. But you can see that there's a big contribution from other processes. So how do we understand that? And this is where we require Richard Dalletz's plot, where because we've got 3 particles in the final state, we could plot the energy of one against the energy of the second against the energy of the third. There's some energy conservation, so events have to lie inside this triangle here. There is momentum conservation, so events have to lie inside that circle here. And we know that if we had a sequential decay, that the alpha particles along this axis here should have epsilon 1 energy of 0.5. And because there's 3 ways that you could have this decay process, that forms a triangle. And there you go. So there's now the spectrum plotted along that axis, and you can see that actually this component here could be made up of these 2 contributions as well. If it's a democratic decay, then the phase space is filled evenly. If it's a decay of a BoseEinstein condensate, then the event should sit right in the middle. All right, so here's the experimental data. You can see that we have this lovely sequential decay and one event, perhaps, that one would characterize as a BoseEinstein condensate. And if one wants to do a proper analysis on this, what one does is fold it up. And because of the symmetry, you can project everything onto a single axis and then fit different contributions to work out what is the probability that you've got this 3-body decay versus 2-body decay. And we can reach a branching ratio which is less than the 0.06. So we are now below a limit which shows that probably this is not a Bose-Einstein condensate. So we have a structure which looks more like this than this. And I've probably run out of time.
No, it's about 4 minutes.
Oh, OK, but that's not enough. So I'll cut through the molecular stuff. That was lovely stuff. But I'll go to my conclusions because Mike's left. And if Mike's left, then there's no point continuing. So what we see here is that picture that we had right back at the beginning. We have now an understanding of the structure here and the, if you like, the topology of the carbon-12 nucleus. We can now map that against Nick Manton's skyrmions. So we, in fact, here is the skyrmion which is associated with carbon-12 and indeed the Hoyle state. So the Hoyle state has this kind of triangular structure, just like you see in that skyrmion picture. And therefore, you might conclude, ladies and gentlemen of the jury, that because the Hoyle state is associated with life and that we can describe that Hoyle state in terms of this skyrmionic topology, that topology is at the heart of life. Thank you.
Problem in QCD, namely confinement. Is that correct?
Say it again.
The topology that you're talking about seems to have little to do with the deep problem of confinement.
No, I would agree with that, yes.
Okay.
Is that a criticism or an observation?
I just want to make sure I'm following you.
Yeah, no,
okay.
You got that right.
Oh, yeah, I got that right.
Yeah.
Okay, it's a higher level.
Yes.
Higher level interactions beyond the QCD scale are giving rise to this topology.
That's right. So remember the strong interaction on the nuclear scale is different to the strong interaction on the subnucleonic scale.
Right.
And historically, on the nuclear scale, it's been described by the exchange of mesons of various kinds. And on the subnucleonic scale, it's described by gluons.
Right.
Okay, so the degrees of freedom are different.
Okay.
How good is the scope?
So how good is the skyrmionic picture?
Compared to these?
It's so what have they done? So remember the skyrmion is a classical object. So it's not a perfect description of a quantum system. So what it has embedded in it is the symmetries, and so the symmetries cross over.
Well, it's I guess it's some kind of analog of a superfluid flow pattern, like
Yeah.
vortices in it. So.
Yeah. So what it's mapping out is the shape of the pion field, and hence how the particles would arrange themselves within that pion field. What you can do is not only look at the shapes, but you can calculate energies from the skyrmionic picture. So it's you have to fit to a few things. So you have to fit to the binding energy of the deuteron, and I think they also fit to the binding energy of lithium-6. But following that, you can make a prediction based on different skyrmionic configurations. What are the energy levels in the nuclei? And it's not bad.
So the coil state is that kind of threefold looking thing at skyrmion?
Yes.
The third one or whatever?
Yeah.
I mean, are there any big failures? I mean, does it really can you really assign all the kind of states to different skyrmion
Skyrmions, the way it's configured here is looking at the alpha particle-like nuclei.
Yeah.
So if you want to break open a skyrmion and add another degree of freedom, it's not quite so good. So if you think about going from carbon-12 to carbon-13, the description's not so good.
So your little kind of almost chemical-like blocks, I mean, it looks like you've got in the chemistry you've got directional valence bonds and things to give these shapes. There's no aspect like that in the nuclear force, right?
No.
The skyrmions are somehow field is giving you a genesis of shape.
Correct. There is some phase information, so you can see the colors here determine how the skyrmionic field changes around the faces of that cube, and then that gives you some rules about how you can put the blocks together. But beyond that, it's not much more complicated. You should invite Nick to come and give you a talk. He's an enthusiast.